Hello guys. Moment distribution. Frames. No sway. What means by no sway or no sideways movement allowed? You see, it's restrained. You don't have any possibility of this moving side to side. That's why it's called no sway or no sideways allowed. So no sway. First step. We did this, by the way. There is a video of this in using slow deflection, and it was a fairly good amount of work. But imagine this once again. I always do the same thing. I always ask the same thing. Can you imagine this solved by the method of the forces? So you have 3, 6, 7, or consistent deformations, which is the real name of the method. You have 7 here, 7 unknowns. That means that you have to select 4 redundants and work with 4 different combinations of deformations. Now, if you use the moment distribution, as I explained before, the first step is determining K, the stiffness, the bending stiffness of the members. What is the K when the far end is fixed? I have that handout somewhere, and you should have it also in the video that is called assumptions and concepts, or something like that. Conventions and assumptions for this method. But when the far end is fixed, the K for the member is I divided by L. L is 15, so this K is going to be I over 15. Now, when the member is fixed like that also at the end, then it's the same thing, K equals I over 15. Now, when the member is a pin, the far end is pin, then this is 3/4 of I divided by L, and L is 15. Which is the same thing as saying 3 over 60, which is the same thing as saying I over 20. So now we have all the K's. Good. Done. Look how fast that's it. It shouldn't take time from you. Now the second step is finding the distribution factors. And the distribution factors is the K of the member that we are trying to find the distribution factor for, divided by the summation of the K's. For all either absolute K or relative K is the same thing. Remember, absolute K is the K with the bar, relative K is the K without the bar. So when we want to do that, then we start any joint, but you know the distribution factor for B is going to be 0, given the fact that this is a fixed support. The distribution factor for A is going to be also 0, AC. And the distribution factor for D is going to be 1, given that this is a pin in this part. However, we're going to be using a bunch of simplifications for that. But let's put it here. Distribution factor BC equal distribution factor AC, and this is 0 because it's a fixed support. The distribution factor DC is 1 because it's a pin support. It's a pin connection. Now we need to find distribution factor CB, CA, and CD. Distribution factor CB, distribution factor CA, let's say CA or CB. CB is the K of CB, which is I divided by 15, divided by the summation of K's. So I divided by 15 plus I divided by 15 plus I divided by 20. And when you do that, the distribution factor is 0.3636 something, so 0.364. That's it. Now the distribution factor CA, this one, is I divided by 15 divided by the summation, which is basically the same value that we have here, so 0.364. And the distribution factor CD, you don't have to calculate it because it's 1 minus the summation of these two. Remember, the summation of all the stiffness of the bending stiffness of the member has to be I, 1 in this case, but you can calculate it. So in this case it will be I divided by 20, which is the bending stiffness of this member, divided by I15 plus I15 plus I20, and that value is going to be 0.273. Let's check. 0.34 times 2 plus 0.273 plus 0.72, 0.993, but yeah, I mean 0.993 is not 0.72, it's 0.72a, so 0.364 times 2 plus 0.273, 1.001. That should be 1, but because we are rounding, that's where the errors come from, which are small errors, but you have to be able to identify those errors and detect, are those errors for real or did I mess up? Okay, the next step is building your table for distribution, and you have to build that table in the way that you feel more comfortable or most comfortable about. I like putting all the members that share a joint together if it's possible. So I start with joint, and then I say join, and then you're gonna have the first joint that you have is a joint B here, and then the member, I'm gonna put the member here, so this is the member BC. Now that joint B is connected to the joint C, so I'm going to put the joint C here, and that joint C has CB, which I'm gonna put here close to the joint B, because this is the way I see it, right? Both of them should be close to each other. Then I'm going to put CA. You can actually try to put CD and DC if you want to. I'm gonna put CA. I'm gonna put CA here. And then I'm gonna put CD. Those are the 3 bars connected to that joint C. But now I'm going to put the joint D, and in the joint D, I'm gonna put DC. But you see something? We are missing something here. We are missing AC, these legs. So I'm gonna put the leg here, right there, and I'm going to put here AC. But then I know this AC has to be related to this CA. I'm gonna do something. I'm gonna do like a flow chart, like that. So I don't keep track of CA and AC are connected in that way. And that's pretty much it. Now I put here the distribution factor and the fixed end moments. Distribution factor for BC. Distribution factor for BC, we already calculated that, or say that it was 0. Distribution factor for CB is 0.364. You should put it here, by the way. Connect both of them together. I'm gonna put it here, CB and CD. I should put it there, not you. It's just my OCD kicking here. 364, and then CA is 0.364. You don't have to do these boxes. I just do it to be sure that that's the distribution factor and not anything else funky going on there. Now CD is 0.273. Which in this case it doesn't matter what way it goes. DC is 1. I mean, this box in my mind, that's what I'm saying. Now this DC, where are DC? Where are you, DC? DC is the pinned one, right? DC, so this is 1, and this is the stray one, the prodigal son that went somewhere else and came back. So AC here, and that should be 0 because it's the other fixed support here, 0. And now we have the distribution moments, the fixed end moments, I'm sorry. The fixed end moment for that, remember, the fixed end moment for that situation, WL squared divided by 12 in both sides, WL squared divided by 12. So the fixed end moment for that is going to be 2 times 15 squared divided by 12, 37.5. 37.5, and if this is B and this is C, so this one here is going to be positive 37.5 positive moment, and this will be BC 37.5, but CB here will be this one, which is negative 37.5. Now look at this moment distribution. The fixed moment here is 0, the fixed moment here is 0. Reason for that, plain and simple, we don't have any load. If you don't have any load, you don't have any fixed moments for those. Now important, extremely, is this thing here. This is a moment, but that is an external moment applied, and the external moment is applied at the joint C. So you have to be very careful that you have those 100 kip per foot applied at the joint C externally. And if you go back to that video that I explained the conventions, because this is an external moment, and I say, oh, complete this thing here, the way this is pointing is the direction positive or negative of the moment. I already explained that in the other part. That, even though it's clockwise, because it's external, then it's a positive moment that is applied there, not the negative moment. For the internal ones, we are using the convention counterclockwise positive, clockwise negative, but in this case, because it's external, the convention gets inverted. So once we have this, the next step is do what? We have to look for the most unbalanced joint. The most unbalanced joint for this that will be the step 3. No, the step 4. The step 3 is this, fixed moments. So the step 4 will be for looking for the most unbalanced joint or joints. In this case, you have an unbalance here of 37.5. I mean, the most unbalanced joint, let's say not locked. Not locked meaning that you don't have by starters in that joint a fixed support. You can put there not fixed if you want to. So the only one that is unbalanced, if you look at that, is joint C. Joint C. Now joint C needs to equilibrate or compensate for everything, needs what? Needs 100, because this belongs to the joint C, and this is negative 37.5. So it needs negative 62.5. 62.5, right? Let me check it. And this time, my brain at this time is not working full. Minus 37.5. 62.5. Needs negative 62.5 to compensate for that. Now, this negative 62.5 has to be distributed according to the distribution factors at CB, CA, and AC. That's the way it has to, I'm sorry, CB, CA, and CD. The CA will transfer over there, whatever it has to transfer over there. But the distribution factor for the joint C, let me put it here, is everything that starts with C. That's it. 62.5 has to be distributed here. So if I multiply that 62.5 times 0.364, that's going to be 22.75, negative 22.75, which is the same thing transferred to this joint because it's the same distribution factor. Now for this one, it will be 0.6273 times 62.5. That is 1706, 1706, negative 1706. Now let's take a quick look at what is happening here. This 1706 is supposed to be, first of all, this one, or this one, whatever way you want to, this one is now balanced, this joint. You can, with this, you can add the three of them and now the joint C is balanced. That's what we just did here, right? Now this CB, remember, has to transfer the transmission factor or the carry on factor is a 0.5. So this is gonna transfer to this pin support 0.5 of that value. That means that it's gonna be transferring negative 11.375. This negative 22.75 is going to be transferring from here to A. Same value because it's 0.5. This multiplied by 0.5. So this is going to be transferring here negative 11.375. Now, what about CD? This value is supposed to be transferred to CD, but because we are using the simplified approach, with this K, this is a pin support, and at the end I know it shouldn't be receiving anything because it should be that value at D, it should just be 0 the moment in that part. So it shouldn't be receiving anything anyway in that part. So how are we doing this so far? I don't know. DC is a 0, which is what's supposed to be. This joint is balanced, and AC is a fixed support, and BC is a fixed support. So there's nothing to balance here. There's nothing to balance here. Joint C is already balanced, and the moment here should be 0, which means it's already balanced too. So basically this is it. We already finished. So now we use the step 5 is add columns in order to find the final moment or the external moment. So if we do this plus this is going to be 26.125 positive. If we do this is going to be negative 60.25. Notice that I don't take this into account anymore, and I don't take that into account anymore because I already distributed and balanced it through the joints. This is negative 22.75. This one here is negative 17.06. This is 0 because it's the pin, and this is negative 11.375 over there. They can be small errors due to approximations, but that's about it. Now those are the moments. I always like to do some enforce members because I'm going to ask my students to do those also. So then what you have to do is come back here and then do a drawing of whatever you have. And this is what we have. B, A, C, and D. And now we can copy all the moments that we found. Don't forget the loads, okay? External loads here. And the distances are important to keep per foot. There is a concentrated moment. Notice that I don't put that here. That concentrated moment is at the joint, so I put it at the joint. And I don't have any other load acting any other place. So 26.25, that's the first one. 26.25 at BC, and that is positive. So like that, 26.125 positive. Now CB is this one here. So you have that value which is 60.25 and it's negative. 60.25. Now we go to CA. CA is here. CA is negative 22.75. Negative 22.75. Negative 22.75. And AC here, negative 11.375. So negative 11.375 is like that. And then you have CD, and CD is negative 17.06, negative 17.06. And then you have DC should be 0 because this is a pin, and that's it. Now if you want to transfer these, remember this is like that, so it will be acting like this in here. This one is negative, it will be acting positive here. This one is negative, it will be acting positive here. So just for showing you at the joint what happened. Now if you add this plus that, that's gonna give you 100, or in other words, the joint is balanced, the summation of every single moment. What is the next step? Once we have all of the things that we have here, the next step is calculating our shear values. This is a B, and this is a, I call this VC to the left, and I call this VC to the right, but you can call it in any way that you want to. You can call it VCD, and then you have here VD, which is the only one that exists, and it's the same value, by the way, as dy here when it transferred to that part. This VB also is the same value as by when it transferred over there. And now you have this one here, and in this one here you're gonna have this force is gonna be transferred here, and this force is going to be transferred also here. So with these two, I can calculate this force at the end of this one, which is the same force that is applied here, which is the same force that is here, which is the same force that is here, which is the same force that is here. So this is going to be AY. At the end, this AY is going to be equal to this force plus this force. That's what is going to happen there. And you can calculate those values. How? I can start by doing, I don't know, summation of moments here. If I do summation of moments here at this point, then I have positive 26, negative VB times the distance, which is 15, plus 2 times 15 times 7.5 minus 60.25, and you can calculate that value of VB, which is 12.73. And then you can calculate this value also by summation of forces in Y, and that's 17.27, that value over there. And then this value here is 1.14. When you calculate this value, this value is gonna come in this way. And it makes sense because if you do summation of moments here, you have negative 1706 divided by 15. That's gonna be that value, and it has to go in that way. So that value is 1.14. Summation of forces in X, this value is 1.14, meaning this reaction is 1.14. And you put the units, right? The units are kept. What else? This part is almost done. So that means that if I add 17.27, and this was acting like that, meaning in this case it's gonna now change. So if I add that 17.27 and this 1.14, 17.27 minus 1.14, I have 16.13, which is this value, and this value, and this value, and this value, 16.13. Now the only thing that I'm missing is this, and then I have to transfer this, of course, to that one. This is a roller, meaning I cannot have any horizontal force here in this part. So this horizontal force will be completely and entirely transferred here, which will be also transferred here because of that. And what is that value? That value, if I do moment here at this point, that will be that value Positive times 15 minus 22.75 minus 11.375. In other words, it will be this plus this divided by 15, and that value is 2.27, which is the same 2.27 acting here, and it's the same in turn 2.27 acting here and acting here, acting here and acting here, like that. Yes, I have this one with this one, perfect, and this one is going to be acting in that way, and that is going to be also 2.27. I mean, you can do that step by step, and you should do that, by the way, step by step, and everything that I say how to do it, you should go and now you should do it. So moment distribution, do you like it? I love it. I think this is the best method for solving something simple by hand. Forget about anything else. Sadly, and I received that question already from several of my students, can I select that method? Yeah, you can, but you have to do the method that I'm going to ask you. And that method is going to be either force, I mean consistent deformations, or slope deflection, or moment distribution, or the three of them. I don't know, because I might select problems from every one of them. See you later, guys. One more video I'm going to post, and the video is going to be now a frame with sway, allowing lateral movement. That is the part when things start getting a little bit funky, or when you have two stories also, or more than two stories. That's when this method start becoming more labor intensive. However, it's still way simpler than doing something else by hand. See you later, guys.